All right, this video we're going to talk about the valve timing diagram and demonstrate some of the calculations and what happens actually in the engine at the particular time it's supposed to. So we're going to start over here, which is basically what we teach you in level 1, and these are considered to be theoretic strokes. So we start from this side here. We have our intake stroke, moves from top dead center to bottom dead center. From bottom dead center then, after the intake, we would close the valves and have compression from bottom dead center up to top dead center. After we get to top dead center, power stroke would begin and would end at bottom dead center, and then my exhaust stroke would begin because we open the exhaust valve and we would move the piston up to top dead center again, pushing all of the gas out. Now, there's only 2 of these that are actually truly going to be correct, and I want you to remember that would be the center 2, compression and power. And the thing I'm going to say they have in common is the compression has to end at top dead center. The power has to begin at top dead center. The rest we're going to see now that we alter that a little bit before and after the theoretic stroke, by having the exhaust valve or the intake valve begin to open or start to open, and that's obviously always driven by the cam lobe for each respective valve. Now, I've gone ahead and drawn out one here, and again, I'm going to go through it very slowly. So we have our color-coded for our different strokes. Blue will be my intake stroke, green is my compression stroke, red is my power stroke, and black is going to be my exhaust stroke. All right? Now, you can draw the diagram out any way you want. I always like to start at the power stroke. So if we begin the power stroke and we're moving, and remember always that this is crankshaft revolutions. If we move from top dead center, this point here we refer to as exhaust blowdown. And this is the point where my exhaust valve first starts to come off of its inner base circle, and we start to push that valve open in my cylinder head. It is like popping a balloon. There is still plenty of pressure in that cylinder, but when we begin to crack that valve, that pressure starts to rush out. We're going to use that movement of that exhaust gas out through that hole to develop a little bit of inertia with my exhaust gas. So we start with my exhaust stroke begins here. So we'll put a number on it here. When we look at this, because this is happening before where our theoretic stroke would be, this is how we're going to refer to it, right? So I'm going to say that this is opening at 50 degrees before bottom dead center. Okay? We'll keep the numbers fairly simple for the first 1 or 2 times we're going to do this. So this is opening at 50 degrees before bottom dead center. So we have my exhaust valve is opened at this point. We move around. My piston after bottom dead center is now acting as a pump. It is driving the exhaust gas out, and we're going to keep moving my piston up, and we're going to hold that exhaust valve open until we get here. But if we come back to this 18 degrees before top dead center, my intake valve is opened. My pressurized air from the intake manifold now is starting to move across that clearance volume on the top of the piston and actually help push that exhaust out. All right? At this point now, we're closing the exhaust valve and we're not allowing any more of that to go out. But from this, so we go back and my intake valve now is starting, and my piston after top dead center is moving downward. So we're between drawing in and the turbo building pressure and pushing in, we're allowing the air to fill the cylinder, but we're going to hold it open after bottom dead center a little bit longer, because after bottom dead center, when our piston and crank pin have just come past bottom dead center, that first few degrees of rotation actually isn't going to move that piston vertically very much. So what we're going to do at that point is leave it open, because if I have a turbocharger on there, I can get that turbocharger to squeeze more air in than if I had closed it here and then just did my compression. Our compression will actually begin here then. So at this point where I close the intake valve, and we'll call this 35 degrees after bottom dead center. All right. So at this point, at 35 degrees after the theoretic stroke from the bottom, we're going to close the intake valve, and from this point on in the green, we're going to come up and we're going to have compression. And again, as I said, compression and power are always beginning and ending at top dead center. So when I get to top dead center, my piston is no longer moving, and we cannot be compressing the gas anymore. So this, I mean, we know top dead center is an important part in the thing, but when we look at this valve timing diagram, the fact that this line, or the power stroke, begins here and the compression stroke ends here are two key things to remember when you start looking at any valve timing diagram. All right, so if you don't have them identified, you can figure out from this point. The other thing, and again, it's not that difficult, but if you look at it, right, my exhaust is always going to open somewhere down here. Right, my exhaust should always close somewhere after top dead center, and my intake should be before, and my intake should open before and close after top dead center. And we're going to talk about the math now to figure this out. So, we said 50 degrees, 18, 20, 35. So, when we look at the blue and the black lines on here, we can see that they are more than 1/2 of the revolution. So what we are going to do with them in order to calculate the length of those two strokes is we're always going to be adding. When we look at the power and the compression strokes, those are going to be a subtraction. So we'll start with the power stroke, because that's where we started with before. The power stroke is going to be from top dead center to bottom dead center is 180 degrees. So my power stroke will be 180 degrees minus the 50 degrees before bottom dead center when my exhaust valve opened, which is going to equal 130 degrees. All right, so that means my power stroke is 130 degrees of rotation. Okay, so now let's do the math for each of these. You know, when we're talking about this, we know that this is going to be more than 180 degrees, because 180 degrees would be from top dead center to bottom dead center, or from bottom dead center to top dead center. But because my black line is greater than 180 degrees, I know that I'm going to be adding them together. So for my exhaust stroke, all right, it's going to be, we're going to start with 50 degrees before bottom dead center, plus 180 degrees, plus 12 degrees after top dead center. It's going to give me 242 degrees of exhaust stroke. All right, so we've gone from here, added up everything that was related to the exhaust stroke, the 50 from here to here, 180 from here to here, and then the 12 after it. For the intake stroke, we're going to start with the blue line. The blue line starts from here, and again, it is additive intake, and it's going to be 18 degrees plus 180 degrees from here to here, and then we're going to have 35 degrees after bottom dead center. 8, 13, carry 1, 4, 2, 10, 13, 233 degrees. So those are our exhaust stroke and an intake stroke. All right. The power stroke. In order to find the power stroke, as I said, these were added. In my power stroke, we're going to need to subtract. So we know from top to bottom is 180 degrees. So it's going to be 180 degrees minus 50 degrees equals 130 degrees of power stroke. My compression stroke, and the compression stroke really isn't that important, but if we want to go ahead and calculate everything, this is what we're going to do. So we would take from bottom dead center to top dead center would be, again, 180 degrees. We're starting at 35 degrees after the theoretic stroke, so we're going to subtract that 35 degrees, and that 35 degrees then will give me 5, 7, 4, 145 degrees. When both the intake and the exhaust is open, we refer to that as scavenging. All right? So during scavenging, we are basically pushing the air out, pushing the exhaust out and bringing fresh air in. The other way to express that would be valve overlap. 18 degrees before and plus 12 degrees after would mean that I have 30 degrees of valve overlap. Right? So we go 18 degrees and plus 12 degrees equals 30 degrees of scavenging. All right? Now, and I was about to start to say this, if we want to check our work, we've already said up here that we need 720 degrees of rotation in order to have all of these events happen. But when we add up all of these four numbers, we are going to get more than that. And that is due to the fact that we have both valves open at the same time. This is a nice easy number, 30 degrees. When we add these all up, we should have 30 degrees over this 720. So it is a good way to check to see whether your math is correct. And we can do that real quick. We'll go 242 plus 233 plus 130 plus 145, right? So we get 2 and 3 is 5 and 5 is 10. Carry the 1. 5, 9, 12, 15. 2, and carry the 1, 2, 4, 6, 7. 750 degrees, which would be the 30 degrees on top of that 720 that we started. So now I'm kind of sure that my math is correct. All right. So this is looking at one cylinder. All right. And now I'm going to stop the camera. I'm going to get rid of this. If you have a problem with this, you can go back and play it back again. But I'm going to draw out, because we have to take what else would be happening in the engine. All right. The other thing before we do that is I want to talk about valve lead and valve lag. So valve lead and valve lag. We talked way back at the first about the theoretic strokes. What we taught you in level 1. Going to the top to the bottom, bottom to the top, top to the bottom, bottom to the top. But we know that that doesn't really happen in an engine. Valve lead is what we refer to when the event happens ahead of the theoretic stroke. Valve lag is what happens when it's after after what the theoretic stroke should be. So if we look at this diagram, right, the intake valve opening before top dead center would be a valve lead. The exhaust valve opening before bottom dead center would be a valve lead. Back to the intake closing after bottom dead center would be a valve lag, and the exhaust valve closing after top dead center would also be a valve lag. We have just talked about valve lead and valve lag. So that whole diagram is looking at one individual cylinder. What we want to do now is look at how that is going to work with my entire engine. So I'm going to use a 6-cylinder because we're pretty much talking about inline 6 engines for trucks right at this point, but you can use this for anything, and I'll show you how you would do the math at the end of this. So I've left all the numbers on the board here, but we really don't need any of this stuff other than the power calculation. All right? So we're going to keep this number and we're going to use it for this example. So we're going to use 130 degrees is the length of my power stroke. I've drawn this out here, right? And now what you got to think is that we are dealing with a 6-cylinder engine. So my companion cylinders are put together around the outside. If you go back to my power stroke, and we know that it was taking 130 degrees. So let's say that we are at top dead center on number 1 and it is beginning its power stroke. That power stroke is going to power its way down here, but we're going to say, when is my next beginning of power stroke going to happen on my number 5 cylinder, because that's the next one in my firing order? Well, in order to figure that out, we take the number of degrees rotation in which all the cylinders will fire, 720 degrees, and we divide it by the number of cylinders, in this case 6, which means that the spacing around this is going to be 120 degrees. That means that as my crank is rotating, right, 120 degrees after number 1 begins its power stroke, number 5 will begin its power stroke. But because the length of my power stroke on number 1 is 130 degrees, what's going to happen is the power stroke for number 1 is going to start here, and it's going to keep going 10 degrees after number 5 has started its power stroke. And number 5 is going to start its power stroke here, and it is going to go 10 degrees past where number 3 starts its power stroke. Number 3 will start its power stroke here, and it is going to go past number 1 or number 6 that much, and then we'll be into the second half. So then it'll be 6 to 4. All right, but in these areas, in these areas here, we have more than one cylinder is imparting a force to the crank. Now it's not going to be a lot of force, because if you look at number 1 is going to be at the end of its power stroke. Number 5 is going to be at the beginning of its power stroke. We have really not a lot of mechanical advantage with my crank pin at that point, but they are happening at the same time. That is what we refer to as a power lap. If we have an overlap in this, right? So one kind of a general guideline you could look at is if you look at your power stroke and then do the math for your your spacing on your cylinders. If your power stroke is longer than the spacing on your cylinders firing, then it will be a lap. If it's less than that, it would be a lag. Okay? Now, I'm gonna I'll erase this and we'll demonstrate it for a 4-cylinder. So I'm going to keep using the same numbers we started with here. All right. So at 130 degrees is going to be the length of my power stroke. We're going to say this is a 4-cylinder engine. So my beginning of the firing for each cylinder is going to be actually, number 1 is going to fire here at top dead center. And we're going to go, as we said down here, 130 degrees again. Right? At 130 degrees, after top dead center, right, there's going to be nothing imparting any force to the crankshaft at this point, which means that we're basically going to be coasting till we get to bottom dead center. When I get to that bottom dead center, then the next one in the firing order, let's say number 4, is going to start firing, and it is going to go from here to here, which would be again my 130 degrees of the power stroke, and then there would be no input to here. That should actually look more like that. All right. So in this, right, we could say that from here, in this, remember going back to this is 50 degrees before bottom dead center. For that 50 degrees of rotation, there is no force pushing or driving the engine. It is simply the momentum of the crankshaft, the counterbalances, the clutch, the torque converter, or whatever is on the back of the transmission, keeping it moving until the next piston begins its power stroke. All right? The other common engine that we deal with is the 8-cylinder. With that, we're going to say, again, it's simple math. Take the 720 degrees divided by 8 cylinders equals 90 degrees of spacing, which means it would be like this. All right? So, and if we keep using that 130 degrees, we're going to have, from this 90 degree angle, we would actually have a 40 degree power lap. So what we're trying to get through with this is, the more cylinders we have, the smoother it's going to run. With this, if I have my my power stroke lasting 130 degrees, that means I have a 40 degree power lap here. And I would have a 40 degree power lap here, and here, and here. So that's why an 8-cylinder engine, we say, runs a little smoother, because we have more than one force. There is no coasting where there's no input to the crankshaft. Okay, so I've gone back to a 6-cylinder engine again, and I just kind of want to demonstrate what the numbers would look like if we were having a power lag. So I'm using the same 18 degrees before top dead center for my intake valve opening, and I'm using the same 12 degrees after top dead center for my exhaust valve closing. But what I've changed on this one is now I am using 70 degrees before bottom dead center where my exhaust valve starts to open. And if we do the math real quickly, because all we really need to do in order to calculate this is figure out what the power stroke is. So what we would do, we go from top dead center to bottom dead center, which would be 180 degrees minus 70 degrees, which would leave the power stroke at 110 degrees. So now, 720 divided by 6 cylinders, 120 degrees. So if my power stroke is only 110 degrees. It means I would have a 10-degree power lag on this 6-cylinder engine. If this helped you understand the valve timing diagram and how it relates to engine operation, do me a favor please and hit the like and subscribe buttons, and thanks for now. Okay, bye.